Modern theoretical physics and discrete mathematics frequently suffer from an epistemological crisis. Prevailing frameworks routinely rely on ex nihilo construction, building mathematical reality from an unstructured void. Established systems, including Zermelo-Fraenkel set theory and the Standard Model of particle physics, posit initial structures like the empty set or fundamental point particles as axiomatic truths. They smuggle structure into the math before any formal logical operations begin, without explaining the origin or bounding constraints of these foundations. When bridging discrete algebraic recurrences and continuous topological manifolds, classical calculus encounters unresolvable error gaps. Traditionally, standard continuum mechanics dismisses these anomalies as numerical artifacts, floating point exhaustion, or asymptotic failures. The theory of infinity, or TOI framework, argues that these anomalies are not artifacts at all. They represent exact, rigorous topological boundaries, what the system defines as singular resonances. To prove this structural alignment, we will map a fully transcendental equation, one built entirely from infinitely long, non-repeating decimals, and demonstrate how it perfectly collapses into a single, discrete integer, without a single decimal of divergence. Correcting the historical assumption about error gaps is required to model complex systems without smuggling arbitrary, ungrounded structure into the math. To properly execute a topological audit, we applied John Forbes Nash Jr.'s concept of topological friction. In pure mathematics, Nash encountered an aggressive geometric friction while developing the isometric embedding theorem. This theorem is a mathematical proof regarding how intrinsic distances are perfectly preserved when mapping any Riemannian manifold into a higher dimensional Euclidean space. Attempting to forcefully embed rigid discrete constraints into a smooth Riemannian manifold literally shreds the smoothness of the function. This consequence is severe. In functional analysis, this destruction is formally classified as a loss of derivatives. To overcome this mathematical barrier, classical algorithms apply artificial smoothing operators. At each iterative step, they forcefully truncate the high-frequency wrinkles, actively hiding the geometric friction to maintain an illusion of perfection. The TOI framework completely rejects this practice. Under its strict operational mandate, mathematical tension is never discarded. Compression loss and transformative costs must be meticulously logged and conserved as measurable residuals. This accountable residual is defined as typed friction. It encompasses the exact costs of dimensional transformation, such as logged branch data and algorithmic lifts, that demonstrably survive geometric projection. Distinguishing between unaccountable fiction, meaning ad hoc mathematical metaphors, and accountable typed friction, establishes the criteria required to cross the continuous discrete boundary safely. Before calculating the polynomial, we discard classical calculus's traditional treatment of infinity. Infinity is strictly not an unreachable quantitative number, a divergent series, or a passive limit. Within this architecture, infinity acts as an active, generative primitive. It is a boundary event that enforces a strict modality shift the moment a mathematical operation attempts to extend beyond its current structural limits. This diagram outlines that generative process. On the left, the unknowable unknown shows that coherent mathematical structure is carved directly out of an infinite plunum. The precise hinge crossing its own limit is the J13 not infinity operator. It regulates permeability, deciding whether to extend or rebook residual tension. The direct consequence is the J14 golden set. This golden set functions as an active, vibrating parent context sealed by harmonic stability. By applying this exact J-series boundary control mechanism to what classical math would call a divergent sequence limit, we guarantee the isolation of a finite structural invariant. This establishes the physical blueprint for our specific polynomial proof. Our test subject for evaluating the continuous limit is the Tribonity constant, represented by the Greek letter tau, approximately equal to 1.83928. We define this value strictly.
The Tribonacci constant is the unique real root greater than 1 of its characteristic equation, generating an infinitely long, non-repeating transcendental decimal. To explore the continuous discrete boundary, the TOI engine maps the exact powers of this transcendental constant into a cubic polynomial shell. We apply a metric hinge substitution, setting x equal to w times tau to the negative second power. Substituting the Fibonacci identity back into the equation causes the transcendental fractions to perfectly factor down. The expression identically zeroes out. The continuous shell collapses, leaving a single flawless real root, w equals -2. Under classical modeling, this mathematical event is impossible to anticipate. Extreme topological tension, constructed entirely out of infinite decimals, perfectly folded inward. It generated a pristine discrete integer, an absolute zero-friction bubble of distinction carved out of the void. The framework dictates that total topological mass must be globally conserved. If the real root absorbed exactly an integer mass of -2, where did the remaining mathematical tension reside? To track this, we deploy the law of topological mass exchange, a principle outlining how mathematical tension seamlessly migrates across the continuous to discrete boundary. We shift our investigation to an empty 2D graphing plane, mapping the complex phase space to locate the residual friction. The solver returns a precise conjugate pair of complex roots. Determining their absolute structural mass requires calculating their squared magnitude. By executing a linear inversion, we extract a pristine value. The squared magnitude resolves identically to 2 times tau to the negative first power. This absolute geometric value proves a flawless mass distribution. The complex mass perfectly accommodates the exact geometric tension required to balance the polynomial's integer seal. Between the real integer mass of -2 and the complex phase mass, the global identity of the system is flawlessly maintained. There is not a single decimal of unaccountable drift. What classical calculus dismisses as a disconnected anomaly is in fact an airtight structural system. It proves definitively that highly localized alignments obey an incredibly strict conserved internal physics. This proof clarifies the rung 8 transient eclipse, a topological glitch found when evaluating discrete sequences. At rung 8, the discrete integer matrix produced a set of complex roots. Because these specific alignments did not scale linearly across all sequence rungs, blunt classical frameworks dismiss them as a golden ghost, a transient computational error. This split screen maps the complex plane to compare the flawed discrete sequence and our continuous transcendental integer anchor. When mapped, a precise spatial lock emerges. The discrete rung 8 roots and the continuous parent roots mirror each other flawlessly. The discrete integer matrix at rung 8 actively attempted to shadow the geometry of its continuous parent boundary, experiencing severe Nash-Mosier friction in its attempt. Discrete algorithmic illusions manifest as physical shadows cast by perfect continuous boundaries. Continuous transcendental math strictly governs discrete sequence behavior. This evidence leads to a formal update to mathematical modeling rules, known as the apophatic inversion. We must abolish the blunt editorial laws that throw away perfectly sealed zero-friction alignments simply because they do not stretch linearly across all infinite rungs of a sequence. These geometric nodes are redefined as encapsulated realities. They are hyper-localized universes that achieve perfect harmonic lock at one specific isolated coordinate. We identify these coordinates as singular resonances. They act as prime mathematical gateways, where the strict topological limits of one sequence perfectly contour to harbor the precise structural invariance of another. Theoretical frameworks function as precision lenses, uniquely calibrated to hunt for these rare mathematical nodes, rather than enforcing linear uniformity. By tracking topological friction and recognizing the exact conservation of mathematical mass, the continuous to discrete boundary reveals itself as an active, solvable map of interconnected, encapsulated realities.